Hi all. This is going to be lecture 5 of chapter 1 of Numerical Linear Algebra series based on the book written by Professor Trepton Lloyd. So this is going to be the continuation of the geometrical properties of the SVD and other useful utilization of the SVD computations. The one of the best utilization is in connections with low rank, the best low rank approximation of the matrices in terms of true norm and the Frobenius norm. So before that, we see that SVD gives a concept that every matrix can be diagonalizable. It means that if you use the proper basis for the domain and the range spaces, a matrix, any matrices of m cross n or whatever the size it may be, it can be reduced into a diagonal matrices. For example, let us assume that B can be expanded in terms of left singular vectors, and X can be expanded in terms of right singular vectors. And from the previous videos, we know that there is a matrix equation Ax equal to B or B is equal to Ax, and we can use these expressions into this, and we finally end up with that the coefficient of expansion of B can be expressed in terms of coefficient of expansion of X to a diagonalizable diagonal matrix. So it means that A can be reduced to diagonal matrices provided that range is expressed in the basis of columns of U and the domain is expressed in the basis of columns of V. So SPD alone doesn't give a terminology of diagonalization of a matrix. It can also done by an eigenvalue decompositions. A diagonal matrix can be not only of a singular values of the SVD from the SVD, it also can be a diagonal matrix. It can be of eigenvalues, where the range and domain are represented as a basis of eigenvectors. We will come in a later part of video of what is eigenvalues, eigenvectors, and here we will give some brief video that in terms of eigenvalue decomposition, any matrix can be expressed in terms of this, where X is a set of linearly independent eigenvectors and A has a diagonal matrix where the diagonal entries are eigenvalues of the matrix A. So similar to the previous one, we can make a coefficient by expansion for a B in a x in terms of x and also x in terms of x. So utilizing these properties, the vector equation, the matrix equation B is equal to A can be expressed in terms of B dash is equal to A. Here this is eigenvalues are being embedded in the diagonal values of this matrix. So although similarly a diagonalization happens in SVD and eigenvalue decomposition, there is some kind of a fundamental difference between SVD and eigenvalue decomposition. The first is we saw that the range and the domain are expressed in two different bases, left singular vectors and right singular vectors, but an eigenvalue it is represented the same basis represented by the eigenvectors. Another one is usually the left, not usually, the left singular vectors and right singular vectors are orthonormal bases for the range and domain, but not necessarily that eigenvalue decomposition give you orthonormal matrices. Third and a very important property that every matrix can be diagonalizable uh, based on SVD. The reason is SVD, every matrix has an SVD decompositions, but all matrices, even rectangular one, does not necessary to have an eigenvalue decompositions. And eigenvalues are mainly utilized to understand the iterative algorithms, because iterativeness ends up with a power k, and we see that how the convergence will be represented with the eigenvalues or the values of the eigenvalues. If it is between -1 to 1 or something like that, we'll come into the later part of the lecture series. Singular vectors itself related to the behavior of A, how the A itself been represented, how the rank of the matrix, how the norm of the matrix, some kind of sense. It helps us to understand the properties of the A itself rather than to understand the property of A power k. So some of the matrix properties can be understandable by the SVD, which is gives in the various theorems. Theorem 5.1 says that helps us to understand the rank of A. The rank of A is R based on the non-zero singular values, and the range of A can be represented through the R left singular vectors, and the null space of A can be represented to the R plus 1 to n right singular vectors. And the norm of a matrix can be computed by the largest singular value for the two norm. For the Frobenius norm, we can represent the sum of non-zero values of the eigenvalue, singular values of the SVD decompositions. And the non-singular values of A are somehow related to the non-zero eigenvalues of A transpose normal matrix. These are termed to be as normal A transpose A or A transpose. And if A is a symmetric matrix, then singular values are really related to the eigenvalues, like an absolute values of the eigenvalues of the A. And determinant of A can be computed by the eigenvalue decomposition, because the determinant of A directly computing itself a computational prohibitive task, but determinant of A can be one or the other way, can be related to the number of non-zero eigenvalues, product of the non-zero eigenvalues. So what is the one of the crux of the SVD? The crux of SVD is related to the rank one update. So A can be related to the R rank one update matrices. So if it has a rank of R, then every singular vector, the first singular vector and first right singular left singular and right singular vectors can be made as an outer product, and that can be keep on adding, and it gives you a rank. Sum of rank 1 updates equal to number of R. So there are other ways of rank 1 updates. It's also related to the Gaussian eliminations, but this rank 1 update have a special property. The reason is the rank and the sum. Say, let us say that rank we express A as a sum of rank gamma or theta pro updates. This can be less than R. So it means for this number of updates, this has the most preserved the highest number of energies. And what does that mean is, if we have some certain number of updates which is something very, very less than the rank the maximum rank of on the rank of the matrix A. So then what does it mean? That it preserves the maximum energy in terms of the norms. So if we are making an approximation of the A through this rank 1 update, not necessarily to be the full rank update, full rank 1 update. So when we compute this and when we try to find the difference in the norm, this norm this is going to be the best approximations of that number of rank 1 updates compared to any other rank 1 updates. And the reason is, it preserves the maximum amount of information inside this rank 1 update for that number of updates, and the difference is going to be equal to the sigma v plus 1. For example, this value is going to be the R, which is the best rank one. Then this tau plus 1 is going to be the zero value. This value will be a 0, so it means that it gives you best rank approximations. So it has also a geometrical interpretation. What does that mean, interpretation? You know that SVD is related to the transformation of hyperellipsoid. So when every rank update, it introduces the axis, the first rank one update gives you the largest axis, the second one rank update gives you the second dimensional update, and third rank it gives the third update, so that the whole volume of the ellipsoid is maximally preserved for that particular number of updates. So after R steps, that's a full rank, we capture all the information of hyperellipsoid, and it gives you the whole volume of that hyperellipsoid in the geometrical perspective. It helps us in image compression, functional analysis, and noise removal, and so many applications are related to the SVD. Hopefully we'll see it in the later part of the lecture series. So it gives you a theorem one, that for that particular tau value it can be less than R. Then it gives you the best rank low rank approximations, and that approximated low rank approximations, the difference between that will is the max. It will give the maximum approximation for that particular number of updates, and the difference one will be related to the left out singular values. For example, it is a full rank, then it's all this value is going to be the 0. The computation of SVD we will come into the later part of this lecture series, which is based on the computation of eigenvalues. So from the next video onwards, we will be more focusing upon the QR factorization. Then we'll come into the eigenvalues. Then we'll come into the SVD. Then we'll go to the iterative algorithms. So what we have summarized here is 5.1 gives, there are so many SVD applications. One is it gives you it helps us to identify the rank of the matrix. Then it helps us to identify the 2 norm and Frobenius norm, and it also helps us to identify the determinant of the matrix, and it also helps one of the principal applications for everyday problem. It helps us to compute the best low rank approximation through which we can helps in terms of image compressions. It helps in terms of removing the noise from the images, and also it will be a robust algorithm in solving the least square problems, which will be hopefully see in the second chapter of this lecture series. Thank you.